In this video, I'm going to introduce the notion of differentiation to describe the instantaneous rate of change of a function and derive a general expression for the differential or derivative. I will then give an example of differentiation from first principles using the function f of x equals x cubed. Consider a function y equals f of x plotted in the xy plane. There are numerous situations in science and engineering when we want to know what the rate of change of the function is as x changes. Let's consider a point A on the curve described by the function with coordinates a f of a as shown here. The rate of change of the function at this point is defined by the gradient of the tangent to the curve passing through that point. This can be thought of as an instantaneous gradient. It will change as soon as we move away from that point. It's also clear that, provided the curve is smooth and continuous, the closer the second point is to A, the closer the gradient of the tangent at that second point will be to the gradient of the tangent at A. Now, the question is it possible to find the gradient of the tangent exactly for a known function? Well, what we can do is think about 2 points that are near each other. Let's start with our point A and take a point B a distance delta x away from it in the x direction. The coordinates of B will be a plus delta x, f of a plus delta x, because it's on the curve. Now, let's look at the straight line that passes through these points. What's the gradient of this line? We can see that the increase in y, delta y, is f of a plus delta x minus f of a. Thus, the gradient of AB is f of a plus delta x minus f of a divided by delta x. Now, what happens if we have a smaller delta x? In that case, point B moves closer to A. As with tangents, we can see that the gradient of AB gets closer to the gradient of the tangent at A as delta x decreases. Provided the curve is continuous, we can say that in the limit, the gradient of AB tends to the gradient of the tangent at A as delta x tends to 0. Thus, if we can find that limit for a known function, we have a way of calculating the rate of change of f. This is what we call differentiation. We define the differential of a function y equals f of x at a point x f of x as f dashed of x equals the limit as delta x tends to 0 of f of x plus delta x minus f of x divided by delta x. If we have a function like the one shown here, where y equals f of x, then we often use the alternative notation dy by dx equals f dashed of x. Now let's look at an example to see how this works. Consider the curve described by the function f of x equals x cubed. Here we see the function plotted for x values between -3 and 3. Let's take a point A on the curve. If the x-coordinate of A is x, then the y-coordinate of A is x cubed, since it's on the curve. Now, as we did before, we consider a point B on the curve a distance delta x away from A in the x direction. We want to find the gradient of the line passing through A and B. We have the gradient of AB equals delta y over delta x. But what's delta y? Well, we know that the x-coordinate at b is x plus delta x. Thus the y-coordinate at b, which is y plus delta y, must be equal to x plus delta x cubed, since b is on the curve. If we look at the diagram, it's clear that the y in equation 2 is the same as the y in equation 1, i.e. it's equal to x cubed. Thus we have x cubed plus delta y equals x plus delta x all cubed. Subtracting x cubed from both sides, we have delta y equals x plus delta x cubed minus x cubed. Now we need to expand x plus delta x cubed to see what remains. We have x cubed plus 3x squared times delta x plus 3x times delta x squared plus delta x cubed minus x cubed. We can see that the x cubed terms cancel, yielding 3x squared delta x plus 3x times delta x squared plus delta x cubed. To find the gradient of AB, we need to divide this expression by delta x, giving 3x squared plus 3x times delta x plus delta x squared. Finally, we need to consider what happens as b gets closer to a. That is, we let delta x tend to 0. We can see that the gradient of AB tends to 3x squared as delta x tends to 0. Thus the differential, or rate of change of y, dy by dx, is 3x squared. This method is known as differentiation from first principles. In practice, we don't need to do this for known functions, as the result, in this case that the differential of x cubed is 3x squared, is known. However, all of the established differentials have originally been derived in this way. Remember that this result can also be expressed in function notation as follows. If the function f of x is x cubed, the derivative f dashed of x is 3x squared. This has exactly the same meaning as the y in dy by dx notation. As an exercise, see if you can apply the same method to show that the differential of x squared is 2x. And if you fancy something a little more challenging, use the same method to show the more general result for the function f of x equals x to the n.